Okay, so the next thing to do is get editing working. The next and last thing to do, really. So what I want to do is I need to look at how that works again. Rope data structure. So this is something I've got now. I have index working. I have report working in a forwards and backwards manner via stream, and that's nice. But now I need the ability to edit, and this looks like it's defining edits in terms of 4 operations, and if I combine all of them I could get my usual replace operation. And maybe if I'm clever I'll find a way to do replace more easily, like maybe replaces 2 splits and 2 concats. Like this is, if I remember correctly, this is just 1 split and 2 concats. This is 2 splits and 1 concat. So to do a replace would just be at most 2 splits, 2 concats, right? Which would be 4 operations instead of 6 for doing both of these, which I think would be nice. So really the question is just how do I do split and concat? If I can get those 2 primitives working, I can get the whole thing working. Yeah, so this is the part right here that says it scares me, since it says I have to rebalance the tree, which I don't have a ton of experience with. I guess my question to that statement is, does that mean balancing the weights of the tree, or just the nodes? And also, how do you split? It doesn't look like it necessarily has anything about splitting a string in the middle of the string, which I guess you could imagine doing simply by just replacing a node with a leaf node with a branch node and making 2 leaf nodes first, and then you've got your tree set up so you can split the in the node sense. But anyway, so concat doesn't look too hard. It's just a matter of creating a new node, setting it as the root of the 2 that exist, and sticking it in place of the old root. The question I mostly have about that then is, how does that work out in practice if if both of these trees come from the same place? I should look into how split works, because I think that will inform my decisions more. Looks like the most complicated one. S1 and S2. Sure, time complexity. There are 2 cases that must be dealt with. The split point and a string. Right, so this reduces the first case by splitting the string at the split point to create 2 leaf nodes. Yep, that's what I was saying. Okay. For example, to split the 22 character rope pictured in figure 2.3, that's this one right here, on the right, into 2 equal component ropes of length 11. K. So it says to do that, you need to find the position of character 12, which is at the K node, and then remove the link between K and the right child of G. Go to the parent of G and subtract the weight of K from the weight of D. Right, so then you have to like recursively go up and change everybody's weights. Travel up the tree and remove the right links to the subtrees. Covering characters past position 11. Yeah, interesting. That's an interesting issue. So how do you know that somebody needs to be removed? Basically, so you're building up a new rope from the right hand side stuff. By everything you split off, you basically are concatenating into a new. So this gets concatenated in, and then this gets concatenated in, and if you have more, you concat all of it in, and that's fine. So you build that up, and then you have your two separate ropes, basically. As the most rope operations require balanced trees, though the tree may rebalancing after splitting. Yes, 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 yes. Newly orphan nodes can reach by concatenating them together and creating a new parent P. Okay, so so yeah, alright. So I've seen enough of that. I need to figure some more details out about this, because their description here is just piss poor horrible, so it's not really any help. I might find another place to explain it, but at some point you just got to grow your wings and fly for yourself, rather than getting plane rides or whatever, you know? So okay, so this is my new rope, and the picture they have over there is sort of similar to saying cut off this, but I'm curious about like other situations. Like what if I wanted to split here? How do I figure that out? What does that entail? How do I know that I'm splitting there and not there, for example? Well, basically, these are an in-order portion of the uh, string, right? If I go from left to right across the leaves of my tree, I always see them in the order that the text exists. So if I'm doing a split, for example, right here, then all of these leaves must come with me. A split that said I wanted this wouldn't make any sense from that point of view. What is that asking for? If I break those, then I've really split it into this, this, and then all of these in a way that doesn't make any sense. So basically, it looks like you figure out where does the thing you want start, and you say okay, go up one level and break that, and then take whatever you broke off and insert it into like your new thing that you're building over here. So you got your new like temporary root right here, and you just say okay, so concat this thing on at that way, and there's nothing here, and then you go okay, now go up one level. Was I on the left hand side there or the right hand side? Well, boom. If I do that though and I split, for example here, does that still work? I go up one level and I say no, that's fine. Yeah, that actually, if I'm splitting here, I should say, so the split starts in this node. I go up one level, I split him, I go up another level, I don't split anything, and then I go up one level and I split him. How do I know what things to split? I mean, the first one was a right-hand child. Right, the first thing I split was a right-hand child, but after that, when I went up, I didn't split the next right-hand child that I found. I split the right-hand child of the next left-hand child. Okay, so it's like you want to split right-hand sides, right? You're only ever splitting right childs off. You might split this one and this one, or you might split all of these together, or you might split these together, or you might split just this. You might split these together, you might split just this, or you might split just this. And you can see no matter what I'm splitting, I'm always taking right hands off, never left hands, right? Which kind of makes sense, because if you start thinking about splitting left hands, it's just like the other way of splitting, but if you only split one type, it somehow makes sure that you always are getting contiguous groups, or helps to make sure of that. But then, after you break the first one, then you say, okay, don't break another right-hand child until you've seen a left hand. Right, if you've gone, you go boom, break that one off, and then go, oh, that was right, ignore it, oh, here's left, okay, so take its right-hand side. Similarly, if you're right here, you go, okay, I want to split here. Okay, go up one side, oh, that was left, don't break it. Aha, that was right, so there's my first one, right-hand side, break it, and then, oh, that was left, so break its right. That makes sense. Starting, if I want to split here, for example, what do I get? It finds this position, it goes, that was left, so don't break, that was left, so don't break. Oh, here's my first right. So yeah, it's basically like you have a state where you're looking for the next right. And that's where you start, is you're looking for the next right child to break. And then once you're done with that and you find it, you do the break, and then you say, looking for the next left. And then once you find that, that enables you to break the next right that you find. Right, so you start here, and then once you find something you want to break, once found, you break it. And then you start looking for the left, and then once you find it, you go back to looking for a right to break. No, once you find it, you break the right there. Okay, I see it. So there you go. Okay. Looking for the next left, and then that creates this loop here. So you break the first right you can find. and then you go until you find a left, and then you break its right. Okay. Fair enough, so that seems like it's gonna work. Then the only question is, like, as you're breaking things, you've got to do the concat, so it seems like I need to write concat first, because you do some concats to build up the new version of all of these concated together, and then you have two strings that you have split. What do you do with these floating nubs, I wonder? Right, like, what's going on there? I think if I redraw that tree like so, left hand side, right nub, here's a nub, here's a good one, and then some good ones over here. Right, so if this is the situation you're in, then all that's really left is this text here. You'd really like to simplify the tree down to just containing this, right? These nodes here is like, this is the shape you would want at least. So I think what I want to do is have like a function that says look at a node, and if it has a left child, or like it has one child, have a way of reducing that down to just being a single leaf node, you know, so that I don't have situations where I never have a node with one child. Whenever I have that, that reduces down to just a leaf node. And then everything always has this one nub up here that's allowed to happen, the sort of global parent who floats up here, so it's not so much become a leaf node actually, it's more like just take, if I have one X in one circle, take me out of the equation and connect my parent and my child in my place. So that's like the reduced tree to being perfectly binary operation, and that would clean up the left hand side, and then the right hand side gets concated together, and etc, etc. Okay. And none of this does any work to balance the tree, so that's got to be thought about too. But let me start with this concat situation right here. So internal node A, node B. Okay. Like, all of these basically always need the ability to say that they can request more memory if they can't get the thing they need. So if we can alloc a rope node, else request amount equals buffer node count times the size of a rope node times 2. Result equals 1. Return result. And yeah, that seems fine. We do need a way to return this root, I think. So maybe it goes more like that. We find out what our root is going to be, and then well, basically what we want to have is a situation where node A and node B both sort of are willing to ignore their parents so they can... Yeah, so... Gotcha. We need a rope node. I'll take a node and a root node. I think. Maybe not. Maybe not. Actually, no. Okay, so what I need is node equals buffer nodes plus... I'm probably going to use nodes a lot though, so I will take that like so. So node root. This has a left of node A. It has a right of node B. It has a weight of node... Oh, shoot. Yep, we're going to do it that way. Okay, so that's all of that stuff. Where is my... Okay, so left, right, left, wait, wait, and the string start can be set to 0. And for good measure, I will set the parent to 0. That way everything just always gets initialized in a way that hopefully makes sense. And, let's see, Okay, so now A and B both need their new parent. Root. B needs its parent. So that should just plug everything. I don't see anything else that would need to be updated, right? That should do the concatenation pretty simply. Okay, so that's, I'm gonna call finished. It's not self-balancing yet, but what can I say? I can only do so much in one pass. Into position, and then this will output A and B, which are the left and right hand sides of the subtrees post split. Okay. To do this, we need sort of a sub-helper thing. Well, first of all, I can do find where the split starts. So it's like have a node equals find node. And then if the position is, greater than this stuff, then we've got a little issue where we have to do the additional split. We have to do the actual string level split. So to do that, it'd be something like node equals string split, and this, like the other thing, needs a request amount because it could at any time decide that it doesn't have enough memory and needs more. Of course, the tricky thing is if that ever happens, it needs a way to restore the state or something that it had before it found out it needed more memory, right? Like this one up here, if it can't do the concat, won't change anything, which is nice. But this one might not be so simple. And the edit function will definitely not be so simple. Anyway, so to do a string split, I'll give you the buffer, I'll give you the node that I want split, I'll give you the relative position that I want split inside that thing. I'll give you the request amount, and up here I'll enable this result concept. I'll say result equals 0. At the end I will return it, and this will actually come out. Okay, so here's the node. Give me that. Okay, and then if this returns, then I need result equals 1, and I should just do a goto to get it done with buffer split end. Right, so far so good. We can so far guarantee that nothing changes in this buffer as a result of a memory request. Now I wonder, after doing a split, if I have to concat all that stuff, how do I know how many nodes I'm going to need? Like this right here would need one more node. So it's like once the split is going to happen, you kind of want to know if you need another node. But what if my split is deeper and it goes like that? Then I need a node here and here to combine these two, and I'll need another node to combine this whole chunk with this one. And this is before I apply any balancing rules. So it's like for every chunk you split off minus 1, that's how many nodes you will need in order to perform the split. Now if I reduced as I went, that would mean like every time I do a split, I'd get a node back for it too, right? Because if I split there, then that leads to this coming off, which it makes this node reducible, and this node coming off, which makes this node reducible. So I could guarantee that I always have as many nodes as I need, I think, which would be really nice. So I should do that. Okay. That way these only ever require new nodes, you know, in a predictable amount at the very beginning. That way they never make edits that aren't going to be easy to, that are, you know, permanent into the structure of the data before I know that I have enough memory, which will be nice. Concat. Okay, so this is a new function that we need. So we're going to need to get a new space for some string. And if that doesn't work out, we're going to want to request the memory that we need. I'll have to introduce actually a concept of what memory the buffer is expecting. So whenever I send out a memory request, I'll set it to true if it's a string for string memory that I need, and I'll set it to false if it's a node memory request. Okay. Good. Okay, and if we were able to get that new rope string that we need, what I should do right here is say, hey, if the position is, greater than 0, do all this work. Otherwise, don't do anything. Okay. In that case, we can memcopy from the buffer data plus the node string start to the new string start with the amount of the whole way to the string minus this position here. Plus also this position here. Right, great. And I want to set the node to the nodes plus the node index. Okay. So that takes this chunk, moves it over there. Awesome. Only trouble is if I do that now, and I don't have the new, I need 2 new nodes for this to work, right? So it's like I need an A-B situation up here, and I need to allocate both of those. Buffer alloc rope node buffer A, or node A, do some stuff. Otherwise, get B, or do some stuff. And those do some stuffs are basically this again and again. So it allocates the 2 nodes that it's going to need. And what it should do is it says, if it ever fails along the way, free the stuff you just got. That way you don't have memory leaks. So it's like, only keep these things around if we can guarantee that we can finish this operation. If it doesn't get into here, make it like it was when we started, basically. Okay, perfect. And then, it becomes an issue of put the text into the new node. We have these other 2 nodes. So the node that we have has some new information. It now has a string start of 0. String start. I'll store the old string start. No need to get this unless we need it, but I'll store the old string start from that node. And use it here and there. So the node string start should now be 0. Its left weight is now this position here. Its left is now node A, and its right is now node B. Nothing else should have changed. So then what I want is a couple of A-B pointers. Node A, oops, node B, and you have some parent to learn about. Node index, node index, you have, so you gotta set all your lefts and rights to 0. Nice. Set your left weight to 0, both of you. Set your actual weight to position. Set your actual weight to the main node's weight minus position. And set your string start to the string start from the root node. Set your string start to the new string start. Okay. I think that should initialize the new split in the tree. Pretty well. So, string split kind of done. Alright, good. And the last thing I have to do is update node position. Oh, yep, thank you, chat. Those should be B's. And also, this right here, the node pointer that I passed in needs to be updated. Almost forgot. It needs to be node B. Good catch, Holy Shift, thank you. So, yeah, that outputs the new node that needs to be operated on, basically. Okay. And then, it's coming along, and it has the node that it needs to split, and it knows that that node now has... It's not in the middle of a node, it's always on the left-hand side of a node, right? If each of these nodes has some string associated with it, we know that we're here on that string and not like here, right? Which means we're all set to start splitting this by node now, because we have that rule that we came up with the loop. So, in the first state, we're looking for the first time that we're the right child as we ascend. So that goes like this. And then I need a rope node. Come on, there it is. And that will be node index. And I'm going to need a child pointer. This is quite similar to the in order traversal and reverse order traversal that we did earlier. So I take this and say you're the child, and then I update nodes to node parent. I probably want to introduce a pointer to that base of the whole array. So node equals the parent node, and then if child equals the right hand side, else, and that's where we break, because now we have something that we can do the split on. Otherwise, we just continue, but I like to include a little assert that the child does in fact equal the left hand side, just in case we need to catch any bugs that come up from that. For now. Right, so that's looking good, and then right here we know that node now points to something such that its right hand child needs to be split off. And the question will become, what do we do to actually mark that that split has happened? And the idea that I put forward before was that I'll start by taking and freeing, if I'm splitting this, remember there's always this true root up here that I'm sort of ignoring that looks like this, that doesn't have a right. So he thinks he has a parent to this guy, even though he's he's sort of the root, but just so that he doesn't look any different than any other node, he's got this parent here that is the true root, right? And this one is always positioned at the beginning of the list. That's always the 0 root. So when I do this split here, which corresponds to this whole part of the array, or part of the tree, this immediately becomes reducible. So my idea is that I'll save the index to this node some other place, right? I have this guy I'm just storing temporarily. I gotta figure out how to draw arrows that don't look horrible. Boom, boom, boom. Just store him for a while. And in the meantime, I take you and I reduce you. So I basically say reduce him so that these two guys connect directly, free him so that he's now available, and we know that means that there's an available node now, and do I need to do anything else, or do I just say... Well, technically probably what I want to do is after a split, after the first initial split, it's hard to say. If I take him all the way out, then the tree becomes this, with this connection here being the main connection, from there to there. Right? That becomes the way the tree looks like. And I have this floating part, which is always the right-hand side. So the left-hand side is always real, and the right-hand side is sort of floating over here. And that maybe is fine, right? That's a fine way to just say the left-hand side, we keep track of it, and it's just the part that we're splitting off and breaking up a ton of that we sort of have floating over here for now. And we don't even need another node right now. This is like the root, so we don't even have to reallocate it. We free it, we leave it free, and if we're in a different scenario, we might find that we're not splitting let me just permanently add this invisible thing here, because I keep adding it and then taking it back off. So that's actually always there. Say I'm performing my split here instead, right? Then I keep, when I first do the split, I keep my eye on this node here for future reference, and I reduce this one, right? So he becomes reduced and these two connect directly, and he's just out. So that means there's guaranteeably a free node in the buffer now. And then it looks up at this one and says, oh, there's another thing I need to break off. And it goes and says, do I have one of these? And when it sees that it has one, after it does this break, it'll do a concatenation, which means it'll allocate a new node and make that the thing it's pointing to. Okay, I see the picture now. I see the picture that we need to construct here. So this is like the split root is the thing we need, and the split root will start off at 0. That's fine for it to start like that. And then whenever it's time to do a split, what'll happen is it'll say well, the thing that it wants to split is node right. And basically, if node right, if split root equals 0, then split root equals node right, right? Otherwise, what we need to do is say that split root is the result of concatenating, which I don't think that's actually correct. It's more like right, okay. Let me just grab a copy of that because I can't necessarily remember all of it. Okay, try again. Okay, so you want to concat inside this buffer here. The left-hand side will be whatever split root used to be. The right-hand side will be node right. And the new root is output right there. And the request amount goes here. If that happens, though, what we actually want to say is assert, because that shouldn't ever happen, right? We said that there should always be a free node by that point. So if there's not, then something went wrong. Now, how did we say there's going to be a free node? Because it looks like we've written some code and I don't see a free node in there anywhere. Well, the idea is that it should happen here before I do this step. So like this right here maybe needs to get stashed. New split. The new split is whatever we're about to split off. And then I'm going to get rid of all this because we're just going to say that node becomes basically invalid by this point in the code. And then we perform the free up here. Wait. You know, I take it back. There's an even better way to think about this that I like even more. which is that the first time through this does not even do anything that causes an alloc. So the first time through, no alloc, and then a free afterwards. And then after that, every time a split happens, it'll cause one alloc here, but there's already been one free here, and so it balances out, right? So that just means that the concept I need is how to reduce a node now. So let's think about reduction. The idea of reduction is I have my main node up here who gets the special privilege of not having two children. And anyone else in the tree who tries to not have two children has to be reduced and removed from existence, basically. So if you have a situation like this guy here is reducible. And to do that, all I have to say is, hey, I think this guy needs to be reduced, so I'll set his invalid child will get set to 0, so that it is clear which one is not actually a child. And then I'll say, pass this node into a function that says reduce it. And to do that reduction, it says, grab my parent and my other child, my actually valid child, link them up together, and then probably have to pass up the chain the change to the weight that causes, you know? If anything, because it might cause some changes. It seems like it would. Because this guy probably still remembers the weights of what was going on over here before. So that's not too bad. And what exactly that means is I take his parent and push it here, I take his corresponding child and push it here, and then I say, hey, recompute your weight, recompute your left weight, and then go up to the next guy and continue doing that until you've recomputed everyone's weight and left weight. Okay. Looks good, so let's add in that concept. Oh, and then at the very end, of course, free that original node. Hey, Canoogles, how you doing? Buffer reduce node takes a pointer to the buffer. The node in question, and that's it. It takes a parent and child pointer to get all of this done, and I'll probably take a node pointer as well. And I'll take a nodes pointer maybe, and maybe I don't need child at that point. Maybe node will serve as child. So there we go. Nodes equals buffer nodes. Node equals nodes plus node index. And then parent equals nodes plus node parent. And what I want to do is right away I should be able to assert that his parent does not equal 0. Wait. That's not true. No, that's just bogus. It's totally possible for this to be the root. Okay. Not the root, but the second root. The non-special one. Okay, what I do need to do is say, look, if I am the left child, otherwise, blah blah blah. And that blah 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 is more like, if I am the left child, get the, and then it's child index, which I'll have to invent still. Aha. So that is some pretty simple code there that just looks like that. Parent right, child index. Child index. Okay, and then a child index we'll say is the node left. If child index equals 0, it gets set to the node right. So we know we have the valid node, or the valid child, the one that's actually not been zeroed out. We connect the parent to that. The reason I wanted a child node was for this purpose, so I think maybe I'll put that back in just because it simplifies a lot of nice stuff. The child equals the parent. We compute the child index, and the child is nodes plus the child index. Then we set the parent to point to the child, and we need to set the child to point to the parent. We can assert, maybe right here, that the child index is not 0 anymore at this point. Okay, so the child parent is the node's parent. Right, okay. So that's nice. We have those two guys linked up. The next thing to deal with is we need to pass up the chain a recomputation of we need to recompute all of the weights and everything. So basically going up that chain until the parent is null, maybe? Wait, no, that doesn't make any sense. What I should do is say while node parent does not equal 0, so it'll say parent does not equal no. What do I do? Apply that logic. I don't even really need to do this. That's also kind of a waste because I can just go parent, 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 and I can break when Perfect. That's pretty good. Then, on that last node, we're at the very top now, so we can just say the weight and the left weight, which are both the same, are just equal to this. Right? Nice. Okay, so that recomputes all the weights that go up the tree. And the next question is, what's left? I have to free the node. Nice. So that reduces a node out of existence. Then the only trick is when you're gonna do that, it's right here. Buffer, reduce node. The node that you want to reduce is node equals. So basically you have to do the math to figure out what index you're at, in this case. But before that happens, you also want to set the right child to being 0, right? So, like so. Nice. Alright, so we're getting somewhere. I'm gonna go take a quick bathroom break, and I'll be right back. Hello, we're back. So, what did I leave off at? We are reducing the right node, or we're reducing this node out that just got chopped. Does anything else need to be done? Oh wait, so this does one split, right? That whole thing there is what happens to achieve one split, and the trick is right here we found, or no, this does one split. This code here finds where that split needs to happen the first time. But now what we need to do is say, after that we need to find future splits that need to happen. And this is going to happen more than once. So enter another loop, and one thing I gotta do real quick just to make it stop distracting me, because I don't want this if here, debug. Nice, okay. Okay, so that reduces the node, and the split is finished, and the question becomes what happens next. And the answer should be that before that happens here, what we actually want to do is say, well, what is node index storing precisely? Node index is no longer useful, so I can reuse that. So node index is the one we want to get rid of, but I want to change node before that happens to be the parent so that we don't end up inside of an invalid node. So there we go. Now we are sitting at the parent of that node, and after that reduction has happened, so say we're splitting right here, after that reduction has happened, this guy is gone and we just have this here, and we're sitting here, and we know we just, wait. We came up here. Came up here. Maybe I should sit in the child that takes its place, actually. So I do this, and I want to be sitting here. Hello, high fives ghost. Hello. So I'm going to be sitting here in this child afterwards, and then I ascend up, and that's when I start doing the second part of the loop, is looking for the left-hand part that enables me to do another one of those. So I don't want to go to the parent, I actually want to go to the left child before the reduction happens. Perform the reduction, and then after that, a sub loop happens real quick that says, okay, we're looking for, yep, this is C++. We're looking for a node where the left hand, yeah, so we need like a child pointer, which I believe I have floating around. look at the child's parent. So then the next question becomes, what do I need to check? Oh, if I'm left or right. So if the node that if the node's left equals this one, else right equals this one. So if I just come up a left-hand side, I need to break out of this loop, and that will cause me to skip back up here and break the right-hand side of that loop. Otherwise, assert that we just came from wingsuitist, something like that. Yes, that is correct. For semicolon is like a while tree loop. I basically am trying a style right now where I only ever use fors for my loops, because I've noticed a lot of the times when I do while loops, I'll write something like, well, I'll be in a situation where I'm like, oh, this structure here doesn't work, right? Like, this is the super ideal structure for a for loop, right? And sometimes you're in a situation where this just doesn't work. Like, I'm in that situation all over the place here, as you can see. And then you go, oh, well, maybe what I really just need is a while loop. So you don't need any of this, and you don't need any of this, and you have some sort of conditional while. It's like, while thing is still valid, keep doing stuff, right? Something like this happens. And then sometimes at the bottom of thing is still valid, you do something like, oh, and thing is still valid equals, update the thing. And this right here has to be at the bottom. Well, I found that I made like a mistake very frequently where I would forget to put my update at the bottom of the while loop, or I would forget that it was there. And it occurred to me that I'm allowed to just do the same exact thing with a for loop if I do this and this, right? So in a for loop, you're allowed to always just drop anything out that you want. So I don't need that initializer. I can leave it out. And then putting it up here for some reason just helps me not to make that bug as often. And while I'm still writing code, I often switch between wanting for loops and while loops and do loops and blah, blah, blah. So I just go with for semicolon, semicolon, and if I need something in those spaces, I put it in, and if I don't, I leave it empty, right? So right here, there's like 3 different loops that are all basically while true loops. And it's just a style I'm trying out, which so far I'm thinking maybe is good for me. I think it makes it's a little easier for me to deal with for some reason. Okay, so then the next thing I need is to assert that in this situation, if we weren't the left child, make sure we're the right child, because if not, we have some kind of bug, right? Now, I'm an idiot. I know you wouldn't necessarily guess that just at a glance, but I am, because I can't compare pointers to integers like that, so I have to do that. Okay, so that'll make sure I find the right spot and get out. And then I'll come back to the top of the loop and continue, but how do I ever get out of the big loop? And the answer to that should probably be, I'm going up, right? I go, oh, that's a right-hand child. I don't do a split. There's a left-hand child. I do a split, and I do a reduction here, and I end up inside this thing, and then I go up. What should happen is, if I ever find myself in the rootest root, I don't do a split there, because there's nothing to split, right? So basically, if I find a spot where equals the root, and since root is always at 0, this checks if the node is the root, then I break out of the big loop, right? So I've finished finding all of my splits at that point. Cool. So at that point, the split root should contain the complete concatenated result of everything that got split out. So he got split out, and then he went up here. He's gone, and these guys connect like this, and these guys got concatenated into one big tree. And then the trick is I've got some other node here that's connecting them, and I just need to take this guy and concatenate with the whole left-hand side of the tree, and then we're done. So am I guaranteed that that concatenation will be possible? Yes, because I have one spare free. I always free one more than I needed to build this right-hand side thing, so then finally that last free node is available here. But why would I do that? I don't want to split and then just recombine everything. That doesn't make any sense. What I want to do is output node A and node B. Okay, cool. So, come on, node A and node B need to go out, and their values should be, node A would be the left-hand child of the super root, and node B would be the split root. Cool. So, just to review, I can now split things, and I can concatenate things. I should be able to write my replace now. Now, obviously, none of these are doing rebalancing, and I'm also not doing merging, so when I get like to a point where this is like 10 characters and this is 20 characters, they could easily fit inside of one string. I'm never doing anything that frees rope strings once I allocate them. And the way to free them would be to say, like, this right here is small enough now that it could be reduced down to just a 30 here. So obviously I have to do all kinds of work to optimize this one to make it reasonable, but getting it working looks like it wasn't that hard, and we're getting there now. Reduce node. I need an example of the interface for replace range. There it is. Okay. In order to replace one range, what I need to do is split between that range, split on that range and on that range. And in order to do that, I should split the right-hand side first. So that looks like buffer split. Let me grab a copy of that signature real quick. So I need a pointer to my buffer, the position where I'm splitting, the outputs go there, and the request amount. And this is one of those situations where I have to figure out what I'm gonna do if I start getting memory issues. I'll deal with that later because I want to get the logic down first without memory being an issue. Start, and in this case I want the left hand side and throw away, and request amount can go there. And again, memory question mark. Okay. And then after that, I have left and right. I just need to take my string and I need to basically build a tree out of that, which will be interesting. I don't have that operation yet, but we can do that. Middle, it'll be like build tree buffer. Here's the string you want. Here's middle. Here's request amount. Right up at the top, I should include a shift amount equals length minus n minus start. Okay, so build tree isn't the function we have yet, but we'll get around to it. And that also asks memory, question mark. And then let's see. So that builds the tree, puts it in the middle, and then I want to concat those together. Concat buffer left and middle buffer concat. And I need an output there. So left and middle will go together, and they will get stored in throwaway, I guess. And we need a memory question mark there. And then finally one more concat between throwaway and right. And we can store that into middle. And then finally, once that's done, concat, what does concat do again? I can't even remember now. So the thing that has to happen is the root itself doesn't necessarily have the parent that it thinks it has. Right, so whenever you do a concat, you need to set the root's parent. In this case, the root doesn't have a parent because the split root is like floating off on its own. In that case, throwaway is about to get concated into something else, so it's going to get its parent that way. And then the only issue left is middle itself needs to be set up to have a parent of 0, which it will have. And let's see, middle of 0 has a parent of 0. So really all that's left is the buffer nodes left needs to become middle, and buffer nodes, let me just make a quick node pointer for this one since I am going to use it a few times. Nodes weight and nodes left weight become the nodes middle dot weight. Cool, cool, cool. So that gets us most of the way there. we just have to deal with these memory question marks and this build tree problem. So let's do build tree first. Okay, hey Flame Dog, what's up? And we're gonna need the rope buffer, the string, its length, the root, or the out position of this new tree, and request amount in case we need more memory. And now building the tree could be very similar to initializing the tree. So I need to pull that up. And init. Hahaha. Yeah, there's not. It's quite a lot. It's quite a lot of code I have to write before it'll, like, I know nothing will make sense until I finish all of the code. Like, I could test individually buffer split and buffer build tree, but like, I won't really catch any bugs in them until I've put that all together anyway. So, seems like, to me, the sensible thing to do. But I do have to admit this is one of the longer stretches where I've just kind of had a lot of code to write before I could get anything done. But if you're used to it, it's not really horrible news. So we don't need to initialize the free lists again, but this part here is the interesting part. Initialize tree. Somehow, I'd like to think that initializing the tree can be abstracted such that it will work here and here. So this is actually going to go up near end init, and build tree is going to be the same function for both of these. And basically what happens here is this has the output there, node equals buffer node, and that parent equals 0, weight equals init size. Yep. Sure. Right, so building a tree requires scratch memory. That's a little interesting. That's a little interesting, because I don't necessarily usually give scratch memory to the edits. But this totally uses scratch memory to create the stack, which I'm gonna have to do here too, right? This rope construct thing is sort of totally necessary for building a tree. So I think that it's time to say that we're just gonna do that. We're just gonna provide scratch memory. Okay. And the rest of that I think will work out. Let me read this one more time. So we initialize all that. That'll be fine. It'll work. The only thing we have to make sure we do is construct stage. Yeah, this right here will be a little different. Basically, to build a tree, what I would like to do is say, I'd like to say that the first node gets allocated and you push its left and right. I don't know. a tough call. Because building this one, I take that extra node and that makes it easy to build. I don't really want to take an extra node to build this tree. I guess I could take an extra node and then throw it away at the end and return the one beneath it. But then, like this one, what I do I take two extra? I do not know. I could take the extra node outside of this function, and then whoever's outside of the function makes the decision whether to throw it away or not. So it's sort of like you don't specify the out, you say build it underneath this node as the sort of special root. So yeah, you'll just pass in a thing that you already have allocated that you want to treat as a root. That should be good, and let me take a quick look at something. Okay. The rest of this, I just need to say that it is going to be kept around but not in play anymore. And instead what this code does is it builds its tree like this. Here's your buffer. Here's the where's the string? Do I have it just called string here, or what's the deal? It's source read and those should be init data, init size. Volubus, all this tree stuff is going on because I'm working on ropes, which, let me pull up right here, is a text buffer type, and for it's you know, it's, I'm not sure that it's popular now, but it's, you know, considered a valid option. At least it was at some point, and there's a lot of information out there where people just say things about ropes that are about like, oh, they're complicated and stuff, and they don't really have any measurements, which is what this whole experiment of mine is about. They say like, oh, it probably doesn't even perform as well as, you know, your standard gap buffer with given caches and stuff like this. So I thought I would put it to the test, and so I have to implement one to actually test how it goes. So while I'm not thrilled by the tree, it's not the worst thing ever, and it is necessary so that I can test the data structure, right? So that's what all the tree stuff is for, is to implement ropes. The root that I want to use is 0. Here's your scratch and your scratch size, and the request amount will be 0 here, because I want to say that this version doesn't have the right to request anything, right? And we'll say if we get this far, result equals not that, right? So if this thing requests memory, then we failed, and that's that. Wingsuitist, I'm not sure if I'll use it in 4coder. It depends on if it's really, really good. I mean, I'm not thrilled about the complexity of it, but the other one I spent that was even harder for me to do was the multi-gap buffer. Turned out to, so far, this doesn't seem as hard as that, and that could have been like partially just because I spent some time on multi-gap buffer setting up some systems that are making this easier. It's hard to say, like I had my memory request systems figured out that in that one, so this one just can rely on them. But in general, my idea here is that I just want a nice simple buffer that won't be hard to maintain, but that will be also fast. So if this has a huge win over other ones, I'll pick it. I haven't yet started working on my scope buffer, which is the one I'm gonna make last, which I think is going to be most optimized for the things I need in 4coder. But I want to have like this experience of setting up multiple buffers and seeing how they work first. So which one I use isn't clear yet. For more info though on this project I'm doing, you can check out my GitHub right here, where all of these buffer experiments are public domain. So this isn't all of 4coder, but this is my buffer experiment where I'm trying to figure out what buffer type I like best. So if you want to check that out, that is available. Just gotta declare all these variables now. Stage is another one of these. Yep, Jack Ryan agrees. I agree with him about the not trying to debug code before it's all written. I mean, you can like inspect variables and stuff and notice some things, but you're never gonna find the important things before you're done. And it could be that you debug something and set it up in a certain way and like solidify it. Like debugging code is kind of like optimizing it in that you're making it better for one purpose, but you also harden it a little bit when you do it. So you lose some of the flexibility that you have when you don't even know how your code actually is working, and you can like move stuff around in big ways still. Alloc rope node. What's the matter with that, huh? What's the matter with that? Missing semicolon before if. Oh. Fair enough. String start equals node stir start. Request amount becomes request amount. Build tree. Yeah, that function is different now. But it looks like we're past the part I was on. That wasn't working. Okay. Let me finish getting those fixed before I go back to other stuff. Build tree takes a buffer, a string length. Right, so we haven't actually got this idea of a middle figured out yet. We'll have to deal with that a little better. What I could do is like build tree floating, so I can get something a little closer to what I originally wanted, and I'll have to provide the scratch and the scratch size still. I don't know what you mean by overlap bug situations. I would just sort of think like you could debug something and make it work the way you think it's going to work, but if you don't see how that fits into the whole big system, like the thing you care about is that the whole thing works. And you might think like, oh, this is going to cause an off by one error, and so you fix it, and then later on it does cause an off by one error because in another piece of code you were thinking of it as ending here instead of there, or there instead of here, and since you always have to shift around a little bit on the like, is this 0 indexed or 1 indexed stuff, like, it's just better to debug it once everything's there so you can see how it relates to everybody else, rather than trying to make leaps about, oh, I think this component should work this way, without in a vacuum of information about how this component behaves in the whole thing. Alright, so now my edits need scratch memory and scratch size. I'll be right back. Gotta take another bathroom break before I continue. Hello again. See ya, wingsuitist. Thanks for coming around. Alright, so I only have a few more of these left, and now I'm able to focus once again. Buffer concat. Why do you disagree with me on how that function works? Buffer, left side, right side. Oh, request amount. Okay. Okay, now it's just this build floating tree. So what's the idea behind build floating tree, you ask? Well, the idea is there's that whole thing where I have to make an extra node and then build the tree underneath it and then free it to make a floating tree. And I don't really want to code that into this function. I'd like to have a separate one for it, because this one already has, like, the main thrust of this function is going to actually be how to deal with these memory problems, which will be kind of interesting once we get there. So I don't really want to mix that up with this. So I'm going to do a breakdown prematurely, possibly, but it seems right, because it then allows this code to follow this pattern. So internal int build tree floating, and this will look somewhat like the other build tree function, but it needs to have a slightly different interface. String length leading out scratch size and the request amount. Okay, so the job here is pretty straightforward. We'll make like the super root right here. It's just a matter of if we can allocate that. So we need to alloc a rope node and to do that I just say, hey, here is the place where I'd like to store that. If you can't get one, that's perfectly alright. I'll just go ahead and report that we needed more memory than what we had. Yep. Never mind all that extra white space that was going on, that was whatever. It's not a problem. And we have this result set. We ask for more node memory. We tell it how much node memory we want. Next up, we need to say do the normal build tree thing. that point. So that goes string length out, scratch size request amount. And if that succeeds, we'll do some stuff. Otherwise, we'll need to request, well, we'll say pass this on, but in whatever memory it wanted, and also make sure to free the super root. Okay. And then in here, if we successfully build that tree, then what we want to do is we want to say set the out to equal the buffer nodes super root dot left and free the super root. So interestingly, no matter what happens, we free the super root, but I think I'll split them up because they're pretty different reasons. So it builds this tree, and then it returns the the floating root, not the super root that we put there. Okay. Cool. Okay, so that builds the whole tree under super root. And then we get the tree out of that node and free that node. So that seems fine. The only thing left to do now is to deal with all of these memory issues. So first of all, at this level, we find ourselves in a slightly complicated situation, because if it's asking for request amount, that means it's not doing an initialization. If request amount is null, we're initializing, and we just say, hey, there was an error, the whole thing is bunk, you don't have a buffer, no problem. But if we're not initializing, then what we need to do is say, okay, we ran out of memory doing an operation, we need to request some new memory, and we need to restore all of the allocated nodes to not being allocated, which is kind of a blah, but it's what we gotta do. So the question is, how will we do that? Well, first of all, what we can do is we can say set up this request amount. Let's see, this right here is requesting for string, so let me find a spot where that happens. Okay, here's how we request new string memory. What's going on down there at the bottom is an allocation for a rope node. So that looks like this. Request amount. Okay. So that sets us up to actually issue the requests. But like I said, we also need to free all of the nodes and all of their strings that we've allocated in this block, which is not a pretty thing to have to do. we'll do it down here so that it doesn't have to happen in two different, like the code doesn't have to be split in two different places, because it's pretty much the same operation in both cases. So basically what we need to do is, when this happens, we take our stack and we clear it out to 0, and left wait, what was that? We say I'm gonna set those, and later on down here, left 0 right equals 0. So when we're first initializing a node, let's say that we set its left and right to 0 right then and there. So we don't need to do it in here. And that way we can actually see if these things have children while we're doing the free loop. And the free loop is gonna look quite a bit different. We're going to take yeah, so we'll use the same stack, it doesn't really matter. And we'll do stack top plus plus equals buffer construct stage. So that gives us the node that we need to free. And then we want to check and see if it has a left and a right. And that basically goes, if you got a left, then push it on. Construct stage. Node left. If you've got a right, push it on. If you have a string start, then free your string. And then finally, you free yourself. And there's of course the same bug that I had up there, where I have to cache this because I could overwrite the stage by the time we get to the bottom. So it actually comes out more like this, right? And that should recursively free the whole thing, which, you know. And when I say recursively, I don't mean function call recursively, I just mean loop with a stack recursively. Cool. Okay, and then we can sort of say that that means that everything goes back to its original state or an equivalently useful state. And then, well, does it build? Alright, does everything still work that was already working? It should. There's no big reason why it wouldn't. Find the bottom. Find to do. Backwards. Up, down, up, down, up, down. Yep, everything still works. We can still stream the rope in and out. So now, where am I? There we go. Now we have replaced range. We just need to deal with those to-dos, right? There's no more to-dos anywhere else. Just these 5. Now we don't want to ever repeat any of these stages as we go, so what we want to do is sort of like a if buffer edit stage here's an idea. Right, so edit stage starts at 0, it comes in, it does this, and then it increments, it does this, and then it increments, and so on. So we have like a self-made instruction pointer. Ooh, 1 minute. Let me have just a quick, there we go. And, anyway. So we have this sort of ongoing instruction pointer, right? That's where the instruction is really which of these things I want to do. And if it ever gets interrupted, we store that instruction pointer here so that it can just resume from where it left off. So if we're at 0, and then we didn't have enough memory for the split, we request more memory, and we don't increment, and the next time we come through, we do 0 again. And we know that all of these are defined that if they fail to do their operation, they don't, if they fail to do their operation for a memory reason, they don't make any changes, right? I'll go double check that, but the idea was supposed to be if they can't do their operation, they don't make any changes. Right, so result equals 1 there. Yeah, so the only time it does that is when it can't achieve the string split at the beginning. And let's see, the string split, when does it fail? It only fails when it can't do one of these allocs, and yep, it doesn't. It frees anything that allocs that it can't end up using. So yeah, that one doesn't change the buffer if it can't do its operation. Concat, again, the only time it does anything that changes the buffer is if it fails to allocate. And there you go. So looks pretty good. Like buffer concat. Yeah. Checked all of these different functions, right? Build tree floating, build tree, we did all that work to make sure that so if any of these fail, and in other words, if any of them return 1 saying they need memory, then what happens is this says it needs memory and it goes out, and the edit stage stays right here, so the next time through it can do that edit stage again. So all of it works out. Yeah, there's something even more fun we could do here. I'll leave it at this. This is what I thought of first, so it's probably my most natural way to do it. But what you could do is take these breaks out and then set like edit stage equals 1 here, so that you're just relying on the fall through. So it'll just basically be executing a bunch of code in order and keeping track of which stage it gets on. And then if it ever has to resume, it'll resume from the right spot, which would be kind of funny. But I'll leave it at this. I'm so torn because it's like that would actually make the code smaller. Well, no, it wouldn't, but it would take out an extra jump in the loop, and it would be closer to how an actual set of, like an actual instruction pointer would work, more like that. Kind of, not really. It's so important, I gotta let it go. But in the next time I do something like this, I'll remember that I want to try it that way instead. That's what the deal is there. So, if this all works, then bada boom ba, we have everything done. So, let me go, and the only trick now is I've introduced scratch memory to the replace range function, which is going to change some other stuff. Whoops. Well, let me look at buffer abstract. Now, I do not have any experience with Blender. In general, I pretty much don't know anything about computer art. I don't do art on the computer. I'm not okay. So funny story, Canookles. I'm at home right now because my apartment is being remodeled, and my options were to stay in Ann Arbor, which is where school is, and I could be in my apartment between 5 p.m. and 8 a.m. to sleep, and then let's see. So I decided to come home because I didn't like the sound of that, and I can attend school remotely for a week and it won't hurt me too much. And since my birthday is coming up, I thought it'd be a nice birthday treat for myself to come home and get a bunch of work done on 4coder so that I can finish up this experiment that I'm doing. So I'm spending my last week as a 19-year-old at home so I can get this done because my apartment's being remodeled. And uh, it seems like a good trade to me because I've been able to get so much done. Yeah, so I'll just answer all of your programming questions anyway real quick. So, first of all the complex stuff there is just because that's how the memory management works. Like, there's the case that tells you where to go, and the if uh, returns true if you need to do a memory request. Uh, the second question, why not just return the result right inside there instead of going to the return? I don't know. I think the thing is that I've realized when you have returns in the middle of the function, so I've been thinking a lot about code transforms, obviously. And I've also been getting used to using gotos all over the place, so that one maybe I could have just done a return there. But the thing is, when you do the code transform that inlines a function, it has to use gotos. There's no other way for it to do this, right? Because when you inline a function into another function, its return can't actually say return. Instead, you just say take whatever is here and write it into the variable that you're trying to output to. And uh, if you do that here, that's fine, but you still have to get out. Like, your return does write from this variable into another variable, and it has to get out of this computation and get to the end of it. And return also achieves that effect, yes, but when you inline it, you have to use the goto to get out. So I've been using goto just because I have to also use them sometimes for code transforms, and because I'm trying to break my stigmatism since they don't seem like a problem to me. So, yeah, in that particular case I could, but in general, if you can keep your functions always ending with one return and not having returns anywhere else, it's sort of a nice style that makes the code transforms, it's closer to what the code transforms have to do anyway. How many years old in normal years is 19 years old in the fourth dimension? I totally don't know how that works because uh, basically, if you have a fourth spatial dimension, the question becomes which dimension in our world did you trade to get that spatial dimension, right? Like, unless you are just in a situation where someone has benevolently given your universe a whole new dimension, so you have all the dimensions of our world plus a spatial dimension, in which case I can't imagine that time works any differently. But there's a risk involved in living in a four-dimensional world that what really happened was you traded one of your time dimensions for a space dimension, and then the flow of time could be totally different. And I don't really know the conversion, unfortunately. I just know how old I am, so I can't tell you for sure. But we would have to work out first of all whether or not we got a benevolent deity providing us with a superfluous dimension to my universe, or we were just trading one of the time dimensions to make that spatial dimension. Yep, I'm studying computer science at university. That's true. Can't do batch edits yet, but I should be able to do everything else. Alright, let's come over here and see what this thing has to say about the scalpel. Post undo, can't do that until I have batches. Can't do that until I have batches. Can't do that without a batch. Do single edit, this I can do. This I can do. Can't do that without batch, can't do that without batch. Can't do that without batch, okay. One more. I think I've already got all the ones in this file, but I'll try it again anyway. Yep, okay. Okay, so like I said, we have now to introduce this scratch memory. Oh, I haven't implemented provide memory yet. That's an important function, so I'm gonna have to do that. Let me see how long this stream is. Alright, this is gonna be super long if I don't cut it off here and cycle it again, so this is not the end of the stream. I'm just taking a short break to stop the stream, and I'll be back in a few minutes.